Imagine training a cutting-edge AI model to get better at solving complex math problems, right? And instead of actually doing the math, it just starts nervously repeating the word wait like 83,000 times in a row.
Which is just a wild thing to see on your terminal.
Totally. Well, welcome to AI Paper Slop. Today we are tearing right into a brand new paper called Purified OPSD, On-Policy Self-Distillation Without Losing How to Think, by Zhenming Shen and colleagues. And if you are an ML engineer or an AI researcher tuning in, here is your 60-second download of the core insight.
Right, let's get into it.
So, on-policy self-distillation, or OPSD, is this really common technique where you use a privileged teacher, meaning a model that already has access to the final reference solution to guide a student model. But the authors found that when you apply this to modern long chain of thought reasoning models, it just fails catastrophically.
Completely falls apart.
Yeah, and the reason is the teacher relies on the reference solution to essentially memorize shortcuts, totally ignoring the step-by-step reasoning needed to actually solve the problem. So the authors fixed this by creating a clever reference-only teacher to mathematically isolate and subtract that shortcut signal.
Which is super cool.
Right. Then they use Pointwise Mutual Information, or PMI, to turn the remaining good reasoning signal into a clean target distribution. The result is consistent, major gains on the hardest math benchmarks like AIM 2025 across models like Qwen 3 and DeepSeek R1 Distill, all without destroying the model's fundamental ability to think.
And I really want to jump in right here to underline exactly why this is so critical for you right now. If your lab is working on distilling a System 2 thinking model, those models that actually pause and reflect before answering, and you are using standard OPSD, you are almost certainly actively lobotomizing your model's reflective capabilities as we speak.
You're just training the ability to reason right out of the weights.
Exactly. But the good news is, this paper provides the exact mathematical fix to stop that from happening. And the implementation is surprisingly elegant.
Okay, let's unpack all of this. Because before we can really appreciate the math of the cure, we need to thoroughly understand the disease. Like, how exactly does standard OPSD break these thinking models? Because on paper, giving a teacher the correct answer so it can better guide the student, that sounds like standard pedagogy. It's how we teach humans, right?
It absolutely sounds intuitive, which is why it's been a standard practice in knowledge distillation for a while now. Usually, you want a smaller, cheaper student model to mimic a larger, highly capable teacher model.
Makes sense.
So to make the teacher's guidance as strong as possible, you give it privileged information, like the actual target answer, so it can perfectly score the student's attempts. But the empirical findings in this paper are genuinely shocking when you apply this to reasoning tasks.
Yeah, the degradation is real.
Right. So they applied standard OPSD to 4 different long chain of thought models. We're talking Qwen 3.8b, Qwen 3.4b, DeepSeek R1 Distill 7b, and Olmo 7b. They trained them on math data sets. And when they evaluated them, performance didn't just plateau.
It tanked.
In most cases, it actively degraded. The models literally got worse at reasoning the more they were trained.
And we should clarify what kind of math we are talking about here for a second. They evaluated these models on benchmarks like AIM 2024 and 2025 and HMMT 2025.
These are not simple addition problems.
No, exactly. For the listeners who might not be familiar with those specific acronyms, AIM is the American Invitational Mathematics Examination. These are grueling, elite high school and college-level math problems. You cannot just memorize the answer to an AIM question. You need pages of scratch-pad logic. You have to, explore a path, realize it's wrong, backtrack, and try a completely new theorem.
Right, which is precisely why long chain of thought, or long co models, were invented in the first place. They are designed to mimic that human System 2 thinking process. They generate thousands of tokens of internal monologue before ever outputting a final answer.
And this leads us to the symptoms of this disease, which I found to be a fascinating and honestly kind of hilarious detail in the empirical observation. So to figure out what was going wrong, the researchers tracked what they call epistemic markers.
The thinking words.
Exactly. For anyone tuning in, these are specific words and phrases that indicate uncertainty, reflection, or backtracking in the model's output. We're talking about phrases like wait, perhaps, let me think, let me reconsider, or alternatively.
Right. They are the linguistic evidence of search and reflection. When you see those markers, you know the model is actively evaluating its own logic tree.
So the researchers tracked these markers during standard OPSD training, and the results go entirely rogue. On the Qwen 3.8b model, the use of these reflective words just completely collapses over time.
It just disappears.
Yeah, the model basically stops stopping to think. It just blurts out answers.
Yeah.
But on the R1 Distill-Kuhn 7B model, the exact opposite happens. The epistemic tokens explode.
Oh, the weight anomaly.
Yes. Over the training run, they go from about 34,000 occurrences to over 83,000. But here's the kicker, that explosion is almost entirely concentrated on the single word wait. The model just starts spamming wait over and over again in its internal monologue.
It is a completely pathological behavior. You end up with this bizarre bifurcation. You either get a model that is completely overconfident and wrong, or a model that is trapped in a degenerate loop of artificial hesitation.
Just spamming the word wait without actually doing any of the cognitive work.
Exactly. None of the mathematical search that usually follows that word.
It's exactly like a student who miraculously got the answer key to a massive calculus test. And then when the teacher asks them to show their work on the chalkboard, they either freeze up entirely or they just nervously stammer, wait, hold on, to fill the silence.
So they never actually learned the calculus.
Right. They only know the final number. Which raises a really important question for you. Is this just some weird artifact of how they prompted the model? Or is the privileged teacher actively punishing the student model for trying to explore different reasoning paths?
Oh, it is absolutely the teacher's fault. And to understand why, it comes down to the underlying mechanics of divergence minimization in OPSD.
Okay, let's get into the mechanics.
So in standard training, the privileged teacher gets the original prompt plus the reference solution. Because it already possesses the final answer, its probability distribution instantly peaks around the direct, shortest path to that answer.
It has no reason to doubt itself.
Exactly. It has zero need to explore alternative hypotheses, it doesn't need to self-correct, and it certainly doesn't need to externalize uncertainty. So when the student model, which does not have the answer key, starts naturally generating those epistemic markers like let me think, or perhaps I should try a different formula, the teacher's distribution looks at those tokens and assigns them a very low probability.
Because to the teacher, thinking is just a waste of time. It already knows the answer.
Precisely. The loss function then steps in and forces the student away from that exploratory behavior. The teacher acts like a tractor beam, pulling the student straight toward the finish line and penalizing any detours.
Which fundamentally destroys the reflective reasoning capability that long COT models depend on to solve novel problems they haven't seen before.
It just nukes it.
Okay, so the teacher's effectively saying, stop thinking aloud, just write down the answer. Which is terrible advice if you actually want the student to generalize to a test they haven't seen. But to fix a bad teacher, you have to prove mathematically that their lessons are flawed. You can't just point to the symptom, you need the pathology report.
Right.
And this is where the paper transitions from empirical observation to some really elegant math. How do they actually isolate this cheating signal inside a massive neural network?
They did it by decomposing the supervision signal. So, in standard OPSD, the training update is driven by the mathematical difference between the teacher's log probabilities and the student's log probabilities. That total update dictates exactly how the student's weights will shift during backpropagation.
Got it.
The researchers hypothesized that this total update isn't one unified lesson. It is actually a contaminated mix of two very distinct signals.
Right. The good lesson and the bad lesson.
Precisely. First, you have the reference-induced signal. The paper calls this delta ref. This is the shortcut. It's the part of the teacher's guidance that relies purely on knowing the answer key.
And the second part.
Second, you have the inference-transferable signal, or delta it. This is the genuine question-conditioned reasoning step. This is the solid logic that the student can actually pack in their backpack and use at inference time when the answer key is taken away.
And the clever setup here, the real aha moment of their methodology, is how they manage to separate those two signals dynamically. Because in a neural network, behaviors are incredibly entangled. You can't just find the shortcut neuron and turn it off.
No, it's a massive soup of matrices.
Right. So they created what they call a reference-only teacher. They fed the specific model the reference solution, but they completely hid the original question.
Which is brilliant.
So the model knows the answer is, say, 42, and it knows the algebraic steps to get to 42,
Yeah.
but it has absolutely no idea what the actual math problem is asking.
It is a brilliant diagnostic tool. By looking at the token predictions of this reference-only teacher, they perfectly isolate the delta ref signal. Think about it. If a model can predict the exact next token without even seeing the question, that token is by definition not dependent on understanding the problem.
It is pure, unadulterated rote memorization of the reference text. So once they isolated that reference-induced cheating signal, They compared it to the total update that standard OPSD was forcing on the student. And the metrics they found are pretty damning for traditional distillation.
Incredibly damning. They looked at two specific metrics across the training checkpoints, cosine similarity and norm fractions. Cosine similarity basically tells us the direction of the update, right? Like where the teacher is trying to steer the student. Norm fractions tell us the size or magnitude of that update.
And what did the data show?
What they found is that the reference-induced shortcut completely dominates the update direction. The teacher is steering the student almost entirely based on the hidden answer key, not on logic.
And the magnitude is wild. The norm fraction for the bad signal, the reference-induced signal, consistently exceeds 1.0. For the ML engineers listening, you know what that means. The bad signal is literally larger than the total update itself.
Which implies that the good signal, the inference-transferable reasoning, is being completely drowned out. In fact, the data shows that the good signal is either totally ignored or actively anti-aligned with the update direction.
Wow.
Yeah, the standard OPSD loss function is actively fighting against the very reasoning skills it is supposed to be teaching.
Okay, so we have successfully diagnosed the root cause, we've isolated the bad signal, delta ref, and we've identified the good residual signal, delta id. So the obvious engineering question is, why can't we just subtract one from the other and call it a day? Just subtract the bad signal from the total update, run your backpropagation on the weights, and move on.
It's tempting. It sounds like simple arithmetic, right? But if we connect this to the bigger picture of how language models are actually trained, we hit a hard mathematical wall. Language models are trained on probability distributions over a vast vocabulary.
Right, they output probabilities for every possible next word.
Exactly. To train a model, you need a valid target distribution to calculate the loss function. The paper mentions using the Jensen-Shannon divergence, which, for those who might need a quick refresher, is essentially just a mathematical way to measure the distance between two probability distributions.
You want to minimize that distance.
Right. But to calculate it, both sides of the equation must be valid probabilities that sum to exactly 1.
Right. I'm going to push back on the simple subtraction idea because of that exact formatting issue. If you just subtract log probabilities from each other, you end up with a residual array of numbers that isn't a valid probability distribution anymore.
It doesn't sum to 1.
Exactly. Some numbers might be wildly negative, others massive. You can't train a student model on a mathematical ghost. It's like trying to subtract an MP3 audio track from a JPEG image. The format is fundamentally wrong. You need a way to translate that raw, unnormalized residual signal back into a clean probability distribution.
That is the perfect analogy. The format is completely broken. And this is where the paper introduces its primary theoretical contribution using Pointwise Mutual Information, or PMI, as the purification mechanism.
Okay, let's break down PMI.
So PMI is a classical tool from information theory. It has been used in natural language processing for decades, usually to measure how strongly two words are associated beyond random chance. But here, the authors use it in a novel way to transform that residual math ghost into a perfectly well-formed target distribution.
How does that transformation actually work in practice, like step by step?
They start with a clean, uncontaminated base distribution. Let's call it P0. This is just the base model looking at the question and generating its natural next token probabilities without any reference solution contaminating its context window.
Okay, so it's a safe starting point.
Exactly. Then they take that good residual signal we isolated earlier, delta, and they use it to adjust P0. Essentially, if delta, it says a token is good for inference-transferable reasoning, it boosts that token's probability in the P0 distribution.
And if it's a bad token?
If it says a token is a cheap shortcut, it penalizes it. They exponentiate this adjustment and normalize the whole thing across the vocabulary. That normalization guarantees you end up with a valid, clean probability distribution that the student can actually learn from using standard loss functions.
So you take the base prior, which is safe and untainted, and you just nudge its probabilities up and down using only the healthy part of the teacher's brain.
That's exactly it. And what's fascinating here for the researchers tuning in is that the authors take the time to prove this isn't just a clever heuristic hack. Under a KL regularized distillation objective, this PMI formulation is mathematically proven to be the closed-form optimal target distribution.
Let's double-click on that because KL regularized distillation is a heavy term, but it's the mathematical foundation of almost everything we do in modern alignment, like RLHF or direct preference optimization, right?
Precisely. RLHF and DPO use a reference model to anchor the training. You do this so the model doesn't just output extreme alien text to maximize a reward score. It has to stay close to its original human-readable distribution, which is measured by KL divergence.
Got it.
The authors show that if you treat the base model, P0, as your reference policy, and you treat that inference-transferable residual as your pure reward signal, the math perfectly derives this exact PMI target. It isn't just an approximation, it is theoretically optimal.
That is the kind of rigorous grounding that takes a paper from an interesting trick to a fundamental method that scales predictably. So let's bring this down to earth and talk about implementation details. Because anytime you introduce multiple teacher distributions and complex probability transformations, ML engineers immediately start sweating about their compute budgets.
Oh, absolutely. VRAM is expensive.
Right. So what does the actual pipeline look like to compute this PMI target in a training loop?
It requires 3 forward passes at each training step. Now, a forward pass is just pushing the data through the network to get a prediction, as opposed to a backward pass, which calculates gradients to update the weights. Crucially, these 3 forward passes use frozen base model weights.
Okay, let's list those 3 passes for clarity.
First, you run the standard privileged teacher, so that's the prompt, plus the question, plus the reference solution. Second, you run the reference probe, that's the prompt, plus the reference only, hiding the question. And third, you run the base model, the prompt, plus the question only.
So you have your 3 sets of logics, your 3 predictions. What happens next?
You subtract the reference probe log probabilities from the teacher log probabilities. That isolates your raw PMI signal. Then, to make it numerically stable for the GPU, you apply centering. You just subtract the mean across the entire vocabulary to remove any global logit shifts.
And then there's a clipping function, right?
Yes. Finally, to keep the math from blowing up, they use a soft clipping function, capping the extreme values at a threshold of 10.
Wait, I want to pause on that specific number and those guardrails.
Yeah.
Why cap it at 10? What exactly happens in the training run if you don't put those guardrails on? Is there an ablation study on that?
Yes, there is, and it's a vital engineering detail. Sometimes the difference between the teacher and the probe can produce extreme outlier values in log probability space. If a token is incredibly rare, the math can spit out a massive number.
Okay, and why is that bad?
Because if you don't clip those numbers and you exponentiate those raw outliers, your target distribution violently explodes. A single token might suddenly get 99.9% probability, which completely destabilizes your training gradients. You start getting NaN errors, and your training run just dies.
The dreaded NaN gradients.
Exactly. By applying a tan function, a soft curve scaled by 10, any normal token values between -5 and +5 pass through basically unchanged, preserving their relative ordering. But extreme values are gently compressed, capping out at exactly positive or -10.
So it smooths it out.
Right. It prevents the model from experiencing gradient explosions without distorting the actual preference structure of the good reasoning steps.
It's the guardrails on the highway, keeping the training run from flying off a cliff. Okay, so we have a mathematically perfect theory, optimal KL regularized distillation, and a solid engineering pipeline with built-in safety nets. But the graveyard of AI research is absolutely overflowing with beautiful math that doesn't actually work in the trenches.
Ain't that the truth?
Does this purified method actually save the model's mind?
It absolutely does. The empirical validation in this paper is incredibly strong. They ran a sweeping benchmark analysis, which you can comb through in Table 1 of the paper. They used high-quality data sets like DASD 10K and MathCode 20K and evaluated on AIM 2024, AIM 2025, and HMMT 2025.
And the results, did the model stop getting dumber?
They did. OPSD PMI consistently improves over both the base model and standard OPSD across all 4 models and all datasets. Where standard OPSD was causing AIME 2025 scores to bleed out and drop the longer it trained, OPSD PMI not only stops the bleeding, it drives the accuracy significantly up and keeps it stable throughout the entire training run. There is no late-stage collapse.
And for me, the most satisfying result brings us all the way back to the weight anomaly we discussed at the start. We talked about how standard OPSD either crushed all epistemic markers or triggered that catastrophic 83,000 token spam of the word weight. What happens to those reflective markers under OPSD PMI?
We see the total return of reflection. It completely cures the pathology. Under OPSD PMI, the models retain their exact baseline distribution of reflective words.
That's amazing.
The vocabulary doesn't collapse into overconfidence, and it doesn't explode into infinite loops. If you look at the graphs in the paper, the marker distribution for OPSD PMI at step 200 is virtually identical to the natural base model. It proves beyond a doubt that the model is still actively thinking, still exploring alternative logic paths, and still externalizing its uncertainty, all while becoming significantly more accurate at solving elite math.
It effectively filters out the toxic shortcut without killing the model's internal monologue. Now, earlier I mentioned compute budgets. You said there were 3 forward passes. I can hear the infrastructure teams listening right now doing the VRAM math in their heads and panicking.
Yeah, that usually sounds expensive.
Right. What is the actual compute overhead for running this purified version versus standard OPSD? Are we tripling the cost?
Not even close, and this is a crucial note for practitioners. Because those extra forward passes, the reference probe, and the base model use the exact same frozen weights, you don't need to load 3 separate models into memory. Furthermore, because they are just evaluating an already generated trajectory from the student, they do not require backpropagation.
So no gradients to track in memory for those passes. You don't need optimizer states taking up space.
Exactly. So the VRAM memory footprint barely moves. The total wall clock training time increases by less than 10% compared to standard OPSD. For a fundamentally superior distillation target that preserves System 2 thinking, a 10% overhead is an absolute bargain.
So what does this all mean for you, the listener? Let's summarize the core value here. If you are in the business of distilling advanced System 2 reasoning capabilities from massive frontier models into smaller, deployable models, you have to be extremely careful with how you use privileged information. Standard privileged distillation is a trap for thinking models. A total trap. It encourages rote memorization, it punishes exploration, and it destroys reflective reasoning. You have to isolate and subtract that reference-induced shortcut. And this paper proves that using a reference-only probe combined with Pointwise Mutual Information is the rigorous, optimal, and computationally cheap way to do it.
And if we step back and look at the macro picture, this raises an incredibly provocative question for the broader field of AI training. In this paper, a reference-only probe successfully identified and mathematically subtracted out rote memorization during a reasoning task. So could we generalize this architecture?
Oh, that's interesting.
Right. Could we use similar negative probing architectures to isolate and mathematically subtract out other undesirable LLM behaviors during training? Think about things like hallucination loops, formatting failures, or incredibly lazy coding patterns. If we can prompt a frozen model to isolate the pure signal of a hallucination, could we use this exact PMI machinery to cleanly subtract it from the training target without relying on the massive human labeling costs of RLHF?
That is a fascinating thread to pull on, using the model's own bad habits as a mathematical antibody against those exact same habits. That is something to definitely mull over as you head back to your IDEs. Thank you for tuning in to this analysis on AI Paper Slump. As always, we highly encourage you to go read the full paper, Purified OPSD, especially to check out the deep dive math derivations and the full ablation studies on the PMI hyperparameters. Until next time, keep your reference signals clean and don't let your models lose how to think.